Hi, I'm Blake, and this is the Physicist's Guide to Success. So you want to do well in calculus-based physics. Whether you want to become a physicist, an engineer, or even an astronaut, you're going to need to know some physics. However, as some of you may know, physics is hard, and it's not the type of hard that you've seen in high school. Physics has a unique difficulty that separates it from other subjects. Unlike math, physics is not about memorizing a specific procedure that you can replicate on a timed exam. Unlike chemistry, physics focuses on everyday objects and requires you to analyze the situation as if it was right in front of you. Unlike English, the creativity in the subject comes from looking at a situation from a different perspective, not how elegant something can be written in or the subject matter. And most importantly, unlike anatomy, memorizing is not important. You heard it. You do not need to memorize equations. Granted, it is extremely useful to memorize constants and equations with special conditions, but even those equations can be derived from first principles. So what makes physics so hard? Assumptions, problem-solving skills, physical intuition, and organization. Now you must be thinking, how are assumptions or even organization be imperative to physics? Because most of the special equations you use depend on special conditions. For instance, one of the first concepts you learn is kinematics, the study of objects in motion without the use of forces. A standard kinematic equation is the following. X is equal to x naught plus v naught t plus 1/2 a t squared. X naught here is going to be your starting position from a certain reference frame, and v naught t is going to be your initial velocity. And a is just going to be whatever you want, but usually we define it as gravity, which is 9.8 meters per second negative. So if you've taken calculus, you've probably seen this before. As you can see, the units add up to meters, meters, meters divided by seconds times seconds, which is meters. Same thing here. However, you can see that the highest order term is 1/2 at squared. This is because it is assumed that the acceleration is constant. However, if you've taken astronomy before, you've probably seen this equation too. F of g, which is the force of gravity, is equal to g times m1, m2, which are the masses of two objects, and r squared. And r is going to be the distance between the object's center of mass. Intuitively, you see that the force of gravity increases as you get closer to an object's center of mass, meaning that the acceleration is not constant. However, we still use the kinematic equations to model an object falling at Earth's surface. So why? Because we assume that the force is uniform across the Earth's surface. While this is technically not true, the results between using this assumption and using it are very close. Another example is the small angle approximation. Oftentimes, it's too hard to simplify an equation, so physicists and engineers choose to set a special condition themselves. For instance, if you're looking at an object that relates to an angle, like a pendulum, you can assume that if the angle is substantially small enough, that sine theta is equal to theta. Well, how can you even say this? This doesn't make any sense, you know? Well, if it's small enough, if you remember from Calc 2, sine theta's Taylor series is going to be theta minus theta cubed 3 factorial plus dot dot dot. As you know, if theta is very small, this is going to be way smaller. This is going to be a very insignificant term, so we can just say it goes to 0, and these terms will keep on getting smaller. So if you just remove this, it just becomes sine theta is equal to theta. Although this might not seem useful now, it is very useful later on in the semester, especially in a topic called simple harmonic motion. So you can really see how assumptions need to be balanced in order to be successful in physics. You don't want to be, making an assumption about a problem and then for some reason halfway through solving it, you just realized, oh shoot, I can't make that assumption. And you don't want to. Organization is also important because most of the time you have to be a detective and search a problem for useful and relevant information. For instance, let's decompose the following problem. The acceleration of a particle is given by axt is equal to negative 2 meters per second squared plus 3 meters per second cubed times d. Find the initial velocity v naught x such that the particle will have the same x coordinate at t equals 4 seconds as it had at t equals 0. What will be the velocity at t is equal to 4 seconds? All right. So the first part, this one right here, really expresses the equation you want to use. You want to use this to integrate backwards and then solve for v naught. If you want to be organized, what you want to do is you're going to want to make a finds and givens column. This is your, sorry. This is going to be your givens column. This is going to be your finds column. So in your finds column, you're going to want to put down a v naught x and then b v t at 4 seconds. So this is just to see that if the parts that you wanted to solve for, that the question really wants you to look at. Oftentimes you'll get a super hard problem that has one hard part that needs to be integrated into the final answer. Personally, when I was doing a lot of these problems back then, what I would do is I'd solve the hard part of the problem and then I would just submit that as my answer. However, that really isn't what they're looking for. They want to integrate that part back into the total answer. So, for instance, let's say you're talking about velocity. They want the total velocity, but solving in the x direction is going to be very hard. For me, I would have solved for that and just submitted it, but I would forget the velocity in the y direction. If you have a finds column, you can check to make sure that you actually have everything in order and you're actually solving for the right thing. Writing the givens can also help check if you've simplified the equation down to be solved. This one doesn't really have a lot of givens, just the fact that ax of t is equal to -2 meters per second squared plus 3 meters per second cubed t. It makes it easy to see if you have all the variables accounted for in the equation you're using. Thus, writing these things down are vital for not making mistakes. Another important thing is drawing a sketch. This problem doesn't really have a sketch that needs to be drawn, but let's pretend like you're drawing something like a pulley problem. So this is your pulley. Drawing a picture really gives you physical intuition on how things are moving. When this goes down, this is going to go up, and it causes a frictional force that goes this way, and then there's this angle. It really helps to make sure that you have the correct mathematical representation of a situation. Oftentimes, you can't sort everything in your head, so having a finds and givens column and a sketch can really help free up your mind and allow you to really feel the problem on paper. Lastly, you want to have good problem-solving skills and physical intuition. Physical intuition helps to visualize how things are moving and how one thing causes another to move. You can't draw a video of an object moving on paper, so you need to view it in your head. If you're going to become a mechanical engineer, this skill is very vital. Moreover, you must know how changing values of an object affects the situation and how objects move. This will help predict, correctly solve, and check a problem. Moreover, good problem skills are necessary to yield the correct equations. This is both in the form of basic algebra skills and the ability to see how equations fit together to form the right equation for your problem. So yeah, if you're going into calculus-based physics, those are the things you have to be good at or improve upon. Most of the time, classes will not teach you these very important values, so you're going to have to quickly learn them yourselves. Don't worry if these values don't come easily, though. Just try your best to do well and improve. Mostly every physicist struggled in the beginning. Although you may not do as good as you wanted to, you'll get better and better. This is Blake, signing off, and I hope to see you next time.